Yes, so I'm at Griffith University, the same place that Jeff is at. For those who don't know, it's just to the north of here at the Gold Coast and at Brisbane, which is where I and Jeff and Mirko are located. Okay, and so yes, so we have Griffith University Centre for Quantum Dynamics, which is where the work is done in our centre, which is in the Centre for Quantum Computation and Communication Technology. Okay, so yes, as Jeff said, this is my topic, Fundamentals and Applications of Quantum Information and Control. So you might ask, so what is quantum information and control? And my answer would be, it's everything. Everything in CQC2T is quantum information and control. Because quantum information, obviously, is what quantum computers process and what quantum communication distributes. And quantum control is how we make those devices do what they're supposed to do the processing or the distribution. Okay, but quantum information and control is much more than just quantum computing and quantum communication. And so my philosophy for this talk is that other people are talking about quantum communication and quantum computation. In this talk, I want to talk about some of the things which are not those topics, but which fall under quantum information and quantum control. And so this is really an enormous range of topics. And if just to pick a few that I'm going to look at, includes quantum metrology, other areas where there exist quantum advantages, and quantum foundations. So as Jeff said, this is theoretically a tutorial, but in reality, it's going to be more of a sampling of the field, okay? Because, as I said, it's an enormously wide field. I can't really, not everything has the same basis. So I'm really just want to give people a flavor of some of the things which are going on. So I'm going to begin by doing that, looking at, as I said, basically in these three sort of areas. And then in the second half of the talk, I want to concentrate on one particular thing which I think is appropriate in a way that I'll explain when we get to that. Okay, so a sampling of the field. So quantum metrology, as I said, is going to be the first example which I look at. So metrology is just the estimation of classical parameters from making measurements. So what's quantum metrology? Well, it's just when you're doing that, but the measurements are performed on quantum systems. And the implication of that is that quantum mechanics places limitations on how accurately that metrology can be done, how accurately we can estimate those parameters given finite resources. So, for example, there's the standard quantum limit on the accuracy of measuring something, and a very elegant way to formulate it is to think about, which will be familiar now that we've heard Lloyd's wonderful talk on quantum computing, to think about a gate. So we have a gate, which is described here, but it has an unknown parameter in it. So lambda is an operator, phi is just this classical parameter that we don't know, and the idea is we would like to learn this. We want to characterize the gate, if you like. And so in the standard way of doing this, what we would do would be, well, we just apply that gate to a qubit or whatever sort of qubit, whatever sort of system it applies to, make some measurement, and then you just do that again and again and again on a whole bunch of qubits. And from the measurement results, process that and get an estimate for this unknown parameter here. And for this scenario, we can show that the standard quantum limit says that the uncertainty with which we can that parameter is bounded by this expression here. So it's just related to the difference between the maximum and minimum eigenvalues of the generator, and it has a 1 over square root n. Okay, so that's the standard quantum limit, but the Heisenberg limit says that if you're more creative, you can do much better. Basically, you can replace that square root of n by an n, which obviously is a big difference if n is large. So doing things creatively means that you can apply these gates n times in any way you like. So your resource is, in this formalization, the number of times you apply this gate, but now you're not restricted to just applying it once on one system and measuring, etc. You can apply them in any order. They could be, you could create an entangled state and apply it on that. You can intersperse it with controlled unitaries. You can do anything you like, and you get this famous Heisenberg limit. So I say famous because it is famous, but it's also wrong. Wrong in the sense that it's not a tight bound. And so I just wanted to put this up just as an advertisement for some recent work coming out of the center, is that in fact the tight bound, so it scales the same way, it's just a factor of pi higher. So people have been thinking about what the Heisenberg limit in a slightly wrong way for a very long time, and we finally done a completely rigorous proof that yeah, as it's usually described, the Heisenberg limit is not attainable, but with a factor of pi it can be. Okay, so that's an example of quantum metrology. It's a fairly formalized example, as I said, but quantum metrology applies for much more real-world problems, if you like, that we have in quantum technology. So as Lloyd talked about, one of the first things you do when trying to build a quantum computer is to characterize the noise that's affecting your systems. And so that's something which is sometimes called noise spectroscopy, a field called noise spectroscopy. And so this has been the theory for this is being developed over decades, but a lot of the theories make assumptions about the nature of the noise such that it has Gaussian statistics. But that's, of course, not always the case with real noise in real devices. And so some of the theory on this, I think, was done by Gerardo Paz Silva. Yes, over there, with collaborators. And then this experiment was then done just last year, published in Nature Comms, which unfortunately doesn't have Gerardo on it. But nevertheless, it's a very nice experiment showing that with non-Gaussian noise, which they engineer in their system, so this is a trans-1 qubit system, where they, by driving the voltage back and forth at the bottom of the I don't know how to call it, this sensitivity plot here, by driving it with Gaussian noise, the response is non-Gaussian, basically. You get a quadratic relation of the noise to the response, and so effectively it's as if it has non-Gaussian noise. And what they showed, yeah, so in this case, you can't actually characterize a system by, even if you have stationary noise, if it has non-Gaussian statistics, then you can't simply talk about the spectrum of the noise. It becomes much more complicated. You have higher order spectra, and this was the first experiment showing this. So this is a bispectrum, which is the simplest sort of higher order spectrum, and they show that it is possible to reconstruct, more or less, what was put in from the experimental data. Okay, so that's just two examples of quantum metrology. As I said, I want to look now on quantum other areas where you have quantum advantages, or maybe it could be a disadvantage, or maybe after all it turns out the same. And we'll see how that works out. Okay, so as I said, I'm going to begin with advantages. So yes, in general, we could just say that quantum mechanics often makes a difference, okay? From classical information to quantum information, it could be good, it could be bad, it could be not, neither. So an example where it's good, where using coherence or entanglement gives us an advantage in enabling us to do something which classically would be much more resource intensive, is this work here. So this was an experiment done in our chairman's lab, so with Terry Rudolph as the theory collaborator. So the idea here is that you are given, so again, it's a fairly abstract problem. You're given a coin, a not necessarily fair coin, okay, but a coin in the sense that you can only toss it once. And so this is called a P coin, and we can think of it in qubit language as being a mixture of the ground state and the excited state with a certain probability. Okay, so we could, so we're just given one of these coins, we could, of course, measure whether it's in the excited or the ground state. That's not going to tell us what P is. All right. Now, the aim, of course, if we measured it many, many times, we could find out what P is, and this would be an example of parameter estimation. But that's not the aim here. The aim here is to produce a P coin, another P coin, but with a different P. And in particular, where we don't know what the initial P is, and what we want to get out is a new P, which is some function of the old P. So that's what this F of P here is. And so the question is, can you do it? And the answer is no. If you give me one p coin, I can't give you another p coin with a different function of p. But if you give me a whole lot of p coins, then maybe I can to some good accuracy. And it turns out that that's indeed the case. Except if the function of p happens to get close to 1, okay, which would mean a deterministic point there. And so classically, then that's a point where it diverges and you need infinite number of p coins in order to be able to do this problem. And so yes, classically you can truncate this bit and make some approximations, etc., etc. But a creative solution, which Terry Rudolph and maybe collaborators, I can't remember, came up with was to think about what if the problem was phrased not in terms of, not in terms of p coins, but p coins, okay, which is over here, which is where you're given a coherent superposition of 0 or 1 with the appropriate coherent amplitudes. And so in this problem, it turns out that it's actually much more efficient to be able to turn a p coin into a function of p coin. And so these are some experimental results showing how many p coins you need in order to produce a function of p coin where it's this particular function, this lambda-like function here. And although it does become relatively large in the middle, that's actually much less than classically. So that's just an illustration of a completely different type of problem in quantum information where you get an advantage from, as I said, of quantum over classical. Another example, this one not from the center at all, is where, to begin with, it seemed like we had things were fundamentally more difficult with quantum information or quantum systems, but then by being clever enough, it turns out that it's not. And so I'm thinking, as an example of this paper here, which as far as I know still hasn't been published, but it was on the archive, called The Energy Requirement of Quantum Processors, so from some fairly famous names here. So the idea here is how much energy does it take to run a quantum computer, which could actually be a practical question when we're talking about extremely large number of qubits. So a naive calculation when we think, okay, and so energy, we really mean we have to have coherent energy and able to do work. And so naively, if you do the calculation, just think, okay, how much energy does this gate take? How much energy does the next gate take? And just add it all up, you come up with that it takes more energy than you would need to do classical reversible computation. Because in principle, and people are seriously talking about the need to move towards reversible computation in order to deal with the increasing carbon footprint of all the computation that's going on in the world. Classically, in principle, you can do reversible computation with no energy cost beyond the energy to actually just encode the data in the first place and encode the answer at the end. Quantum mechanically, it looked like this was not going to be the case, but then these clever people showed that if you used your battery, so to speak, without throwing it away and getting a new battery, but used the battery successively through all of the gates, then in principle, the amount of energy you require, the amount of work you have to do for your computation is no more than classically if you have the type of computation where you have a classical input and a classical output. So such as Shor's algorithm where you're just interested in getting the answer out, you're not doing the computation to create some entangled state or something, you just want the answer. So yes, so that's, as I said, an example where there was an apparent difference between quantum and classical, but it turns out that by being clever and using resources coherently, sort of similar to the Heisenberg limit idea, that you can get around this problem. Okay, so moving on to the third topic, and how am I, oh, there we go, it's all right. Okay, quantum foundation, sorry. So this, again, is a very broad field in itself, and I'm just going to put a few highlights up. So one is, again, one which it's associated with us, in that Tim Ralph, who possibly will be talking later, or maybe not, anyway. But probably most of you will meet Tim if you haven't already. So this is experimental work done with the Chinese satellite Mencius, is that right? Yes. That we heard about yesterday, was it? Must have been, yes. based on a theoretical proposal by Tim. And so essentially, yeah, this is a class of quantum foundations which is about testing quantum mechanics against rival theories. So essentially, Tim proposed, because, okay, a big open question is how does quantum and gravity fit together? And so Tim proposed a theory which had the advantage of being readily testable, that, that moving a quantum field through a gravitational field could cause decoherence in a particular way that could be measured, in that if you had an entanglement between the Earth and the satellite, and if the measurements were done in a way that the second measurement was, that they were not space-like separated, that then you would get one result, whereas if the measurements were done space-like separated, you would get a different result. And I think in the second case that you would get decoherence. Is that right, Tim? Yes. And so this was then put forward as a proposal for funding, and got up, and the experiment was done, published here just last year in Science, showing that in fact Tim was wrong. Well, no, the foil theory this foil theory has been ruled out, in that the experiment shows essentially the same level of decoherence in both situations. So there's no apparent, this theory at least of how quantum and gravity could affect each other has been ruled out. Okay, so that's one type of quantum foundations, where here obviously quantum information is relevant because we're talking about creating entanglement, manipulating it, etc. A different way in which the quantum foundations and quantum information can relate is for quantum foundations to give a way to understand at the most fundamental level where the power of the quantum comes from. And so there's a lot of work that people, in the most fundamental way, we want to be able to characterize that without talking about quantum mechanics, because we really want to understand, independent of the theory, what is it in nature which tells us how powerful it is. And so this is the idea which is a lot of people working on, of device-independent characterizations of theories. And so I'm highlighting some particular work from Eric Cavalcanti, who's associated with the center with me. And so this was published in 2018. So probably most people have heard of Bell inequalities. And so maybe I'll just start with that as an idea, and I'll talk more about that later. So from the causal structure of space-time, we know that faster-than-light signaling is impossible. Okay, so that suggests that I think I said that backwards. We know that faster-than-light signaling is impossible. That suggests that space-time has a causal structure something like this, that if these are space-like separated laboratories or events in laboratories, that X, we could be Alice's choice, can affect Alice's outcome, and Bob's choice can affect Bob's outcome, but not in a way like this, because that you'd think would give faster-than-light signaling. Okay, but we famously know that this causal structure cannot explain Bell correlations. So what is going on in the world? Well, one possibility is that there is a causal link from X to B, say, for example, that Alice's measurement can affect Bob's outcome, but in a way that doesn't allow faster-than-light signaling. And so what Eric showed is that this is possible, but any theory which tries to explain the world that way, in other words, a sort of a classical type of explanation for quantum phenomena, is necessarily going to be fine-tuned, which means that you have to arbitrarily, finely define exactly what the causal influences are in order to get this no signaling while still being able to get violation of Bell inequalities. So that means that it's very implausible to think that there is any classical explanation of these correlations here. Not impossible, but just implausible. And the other achievement in this paper was to then broaden this idea to contextuality. So this is the Koch and Specker inequalities idea, which is another idea of non-classicality in quantum mechanics, and also relates to quantum computing through the contextuality of magic states and things like that. And again, in that case, there is no, you can't really rely on no fast and light signaling thing because everything is just happening locally. So in that case, it's the no fine-tuning explanation is a really powerful way, I think, to understand what the contextuality in quantum mechanics really means and where that power is coming from. Okay, all right, so that's the end of my, my sort of highlights, my sampling of the field. As I said, in the next part of my talk, I want to talk about, well, I've sort of titled it Quantum Communication and got the wrong way, Quantum Computation and Communication Technology from Applications to Fundamentals. Because what I want to talk about here is another example of quantum foundation in which is going to provide, I'm going to claim, a novel market for quantum technology, which is philosophers wanting to advance experimental metaphysics. Sorry?
Small market.
A small market. Well, I'll be optimistic, but yes. Okay, so metaphysics is a branch of philosophy which is essentially concerns itself with the most fundamental things in the world. So, and we can argue about what those are, but that's the basic idea. So experimental metaphysics is the idea that we can say something about that from experiment. And this is an idea which is related to Bell's theorem, which I was just talking about. It's a term coined by Avner Shimoni in 1987 in this book called Philosophical Consequences of Quantum Theory. And as you can see, yeah, it's a term which has caught on at least to some extent. Okay, so what I have to do is explain a little bit more about Bell's theorem, because that's where, so I'm going to go back and give a bit of a history, and then also, and including also some history about what Eugene Wigner said, and then we'll move on from there. Okay, so Bell's theorem dates to 1964. This is the actual title of the paper on the EPR paradox. But this is the conclusion of the paper, which I think is pretty clear. So he's saying the statistical predictions of quantum mechanics, and this color, this brown color, I'm going to use everywhere where we're talking about actual predictions as opposed to assumptions. So the statistical predictions of quantum mechanics are incompatible with separable predetermination. And he explains what he means. That is, any theory in which parameters determine the results of individual measurements, there must be a mechanism whereby the setting of one measurement device can influence the reading of another instrument, however remote. Okay, so that was exactly this, going from Alice's setting to Bob's outcome that I was talking about earlier. Okay, so that's a pretty clear explanation, but I want to be a bit more formal, and I actually set out some rigorously stated metaphysical assumptions here, because there's one which Bell is just taking for granted, but which is going to be imported later on, which I'm going to call absoluteness of observations, which is just the idea that observations really happen, in a sense, okay? If an observation by an observer is a real single event and it's not relative to some other event or some other observer, okay? Predetermination is, I can give it a technical definition, but don't worry about that because it's not going to last long. And then for the idea of it's not no fast and light signaling, it's more than that. We have to be a bit careful here, but I'm going to call it here local agencies. The idea that for any free choice, and by that we just mean something which is chosen in a manner appropriate for a randomized experiment, so just what we do all the time in physics, or any experiment, right? Can be assumed to be correlated only with events in its future light cone. Okay, hopefully that makes sense to people. So those are the assumptions that together, so we can't say anything about these individually, but together we can say these three things cannot all be true, okay, because of Bell's theorem, and more particularly because we now have experiments which, actually follow all the, have been done completely rigorously and rule these out. So yeah, so the way this works is the theorem is saying that if I consider outcomes, so this is Alice's lab here, this is time going up, this is space going this way, is typical in relativity, is that, yeah, Alice's lab is over here, Bob's lab is over there, Alice's make a choice, gets an outcome, the same for Bob. So the idea of predetermination is that somewhere in the past there are variables in the world which determine those outcomes that Alice and Bob get. Okay, so that's the one assumption. The absoluteness is just that these outcomes actually exist, right? Okay. And then the local agency is, as I said before, is that well, more or less as I said before, but it essentially means that the probability of Alice's outcome, given everything like the settings of both parties and the lambdas, the hidden variables, does not actually depend on Bob's setting. Okay, so Bob's setting can't influence the probability of Alice's outcome, given all those other things. And likewise for Bob. So together, these mathematical constraints, that these probabilities are just either 0 or 1, and that these probabilities have to satisfy these equations, give you constraints on the experimental probabilities, okay, because in the lab we can't measure probabilities that depend on lambda, those are hidden variables, but we can measure probabilities which just depend on the settings and the outcomes. And the point is that these assumptions give you constraints on these, and we can show that experiments violate those. Okay, that's what Bell inequalities are. Okay, so that's Bell. Around about the same time, just a little bit earlier, Wigner was making some, so not a theorem, but I'm calling it metaphysical musings, in this essay called Remarks on the Mind-Body Question. And so I'll just read it through quickly. He says, it's natural to ask about the situation if one does not make an observation oneself on a quantum system, he means, but let someone else carry it out. What is the wave function if my friend, this is the appearance of Wigner's friend, if my friend looked at the quantum object? The answer is that one could only attribute a wave function to the joint system of friend plus object. So this is a superposition, an entanglement between the system and the friend, which he's writing. And he's saying that this follows from the linearity of Schrodinger's equation. This appears absurd, he says, because it implies that my friend was in a state of suspended animation, this superposition of one outcome or the other outcome, before he answered my question about what he saw. And Wigner's conclusion was that Schrodinger's equation cannot be linear, even if it's accepted that my friend has the same type of impressions and sensations as I. So, yeah, so quite an influential paper, as I said, for introducing this concept of Wigner's friend. How does these two things fit together? Well, there was Czeslaw Bruckner wrote this article or published this in 2018, essentially combining Wigner's friend and Bell non-locality. The idea is to incorporate these Wigner's friend into a Bell experiment, and you could get rid of the assumption of predetermination, right? We see like this very strong assumption by, instead of having these hypothetical hidden variables, just have the friend's experiences play the role of those in the theorem. So of course this requires assuming, well, as we'll see, if to get a violation, this requires assuming that the friends actually are in superpositions. So a sort of successful experiment would prove that Wigner was wrong, but yeah, maybe that's probably the wrong way to phrase it, but yes, Bruckner certainly, at least we can say that, certainly assumed that the friend actually could be in a superposition prior to being measured. Okay, so unfortunately, Bruckner's formalization was not really done properly, and so his proof was actually not a proof, so he doesn't actually have a theorem. However, the good news is that there is a proof, a different way of formalizing things, a new proof, and so a new theorem, and that's in this paper here, which again is a collaboration so with Eric Cavalcanti, who I mentioned before, and it also involves an experiment performed in Jeff's lab, and so I think about half of the authors are here, and there were some posters on this yesterday. Okay, there is, as I said, a theorem. The way I'm going to state it here is slightly different from what is in this paper, so don't be too shocked if you go and look that up and find something different. Okay, so here I'm going to say is that what the theorem is that the conjunction of these assumptions is a contradiction. So the point is now we do not have predetermination anymore. We have absoluteness of observations, the same as before. We have local agency, the same as before. But I also have this assumption, which I'm calling superpowers, right? Why? Because sometimes in a Wigner-Friends experiment, the friend is called an observer and Wigner is called a super observer. So the powers that the super observer is going to use, I'm going to call superpowers. And these superpowers are that the super observer Wigner can perform any arbitrary quantum operation on his friend and the friend's environment. So yeah, it is sort of quite a big assumption. But it's not actually a metaphysical assumption. Okay, this is an assumption that we can test in the lab for any given Wigner and any given friend whether Wigner really has these superpowers. Okay, so it's, yeah, but those are what we need to get the theorem. How does it work? Well, it works to begin with a standard Bell type experiment with two observers and an entangled pair shared between them, and they make a measurement. But the difference here is that these observers, they're inside boxes, are just the friends. So on Charlie's side, for example, Charlie is the friend of Alice. Alice is outside the box, and Alice is the one who's ultimately going to record the data that we're going to look at to determine, yeah, the outcome of the experiment. Okay, so if Alice wants to make a measurement, if her setting is x equals 1, so if she's randomly chosen a second setting and it's x equals 1, then she gets her answer simply by opening a window to Charlie's laboratory and asking Charlie what he saw, and then Alice just writes down the same thing. Okay? On the other hand, if she wants to know, so that's either if her setting is x equals 1, but if it's something else, right, then she does something completely different, which is after Charlie has completed his measurement, Alice wheels up this super device which reverses time in Charlie's laboratory. So that after she applies this for the appropriate time, Charlie's measurement is undone. Charlie becomes unentangled or uncorrelated with this quantum particle. Then Alice throws Charlie away, takes the quantum particle and makes her own measurement on it. And that's how she gets the outcomes for any other settings other than 1, so 2, 3, etc. And then the same thing is happening on Bob's side with Debbie. And we also arrange these in space-time in a way that these again are space-like separated, and these are on, yeah, it's more or less as you see it here. So the idea here is that the assumption of absoluteness of observation, now the point is that this is meant to apply not just to outcomes A and B, but also to the outcomes that Charlie and Debbie got C and D. We're going to assume that they really got outcomes. Okay, even if you don't know what they are, they really happen. So that means that there exists some joint probability distribution over those outcomes, A, B, C, D. Moreover, we know that if Alice chooses setting 1, that the outcome, her result, is just going to be equal to Charlie's result C, and likewise Bob, if he chooses setting 1, then his outcome is just whatever Debbie saw, D. So that's so we don't have predetermination anymore, we just have these equations here. Local agency is basically the same as before. And these two assumptions, just for ease, we're going to call the assumptions of local friendliness. Okay, so it's not local predetermination, it's local friendliness. And it's different, as we will see. So this metaphysical assumption, joint assumption of local friendliness, again implies constraints on what Alice and Bob can see in their correlations if the superpower that we're assuming they have actually exists. Oh, sorry, I shouldn't say that. It implies constraints, and if the superpowers exist, then those constraints can be violated. Okay, we can get a violation of the inequality which we derive from these constraints if they can do this time reversal, etc. And so basically what the assumption of superpowers here means is that the probabilities that Alice and Bob get from their measurements once they undo Charlie and Debbie's measurements is approximately the same as if Charlie and Debbie had just never been there in the first place. Okay, it doesn't have to be exact, it just has to be good enough to get a violation. And so this is basically our new theorem. How's my time, Jeff?
You have 8 minutes.
Including questions?
No.
Oh, okay, cool. Right, so that's the theorem, but obviously with half the paper authors being experimentalists, you're going to expect to see an experiment, and so here is one. So this is it. Well, this is an experimental diagram at least. This is what happened in a theorist experiment. Okay, in the lab. So I should mention Nora Tischler, who's here as well, who's one of the senior authors on this paper. So we start with a pair of photons entangled in their polarization, sent to separate labs. Okay. In Charlie's lab here, Charlie makes a measurement. Now, what do we mean by that? We want this to be a reversible measurement, so Charlie's not a real friend in the lab. Charlie is just going to be another degree of freedom of the same photon. So Charlie here is the position of the photon, and the measurement of the polarization of the photon is the creation of a perfect or near perfect correlation between the position of the photon and its polarization, which happens with this optical element here. Sorry. Remember what it is? Okay. Okay, so if Alice wants to measure x equals 1, or she's randomly chosen to measure x equals 1. That means she just has to ask Charlie what he saw. Okay, and how does she do that? Well, she just looks to see where Charlie is. So, in other words, she puts a mirror here and then just detects whether Charlie was in this path, in which case Charlie will end up over here, or in this path, in which case Charlie will end up over here. Okay, so that's asking Charlie what he saw. If Alice wants not that to happen, she has to undo Charlie's measurement, which she does by not having a mirror here, but instead reversing all these optical elements here, so that at this point, Charlie, the position of Charlie, there is only one position that Charlie can have, and so there is obviously no correlation with the polarization of the photon, but the polarization of the photon here is almost exactly the same as it was there. That's the reversal. And then Alice just goes and measures the polarization of the photon in any way she likes, okay, which is this measurement over here. And the same thing is happening on Bob's side over there. Okay, so that might look like a theorist version, but these are real experimental data, and I'm not going to have time to explain what all of this means, but I guess the important points is that that local friendliness assumption is not the same as Bell non-locality. So you actually get different inequalities in general, but nevertheless those new inequalities can be violated, and we violated them. And also what we prove is that the set of local friendliness correlations is strict. Oh God, which way around is it? Harder to violate than the set of Bell violations, but Bell correlations, I should say. So that means that it's possible to show Bell non-locality with this system. That's with stronger assumptions, right? Even when it's not possible to show local friendliness. And so these data also illustrate that fact of the theory. Okay, so typically when I've given this talk, people are still a bit confused about where is the friend in this apparatus. So just to reiterate, in our experiment, the friend is a qubit. Okay, just a single qubit, a binary degree of freedom, the path degree of freedom of this quantum particle, the photon. So you might very well ask then, can a qubit really be your friend? And also, didn't you say that you needed superpowers to do this experiment? So, all right, so obviously no, a qubit is not a real macroscopic friend, and that's why we don't need superpowers. We do need considerable powers. I don't want to underestimate the experimentalists, but we don't need superpowers. So the point is that this paper is not a Wigner's friend demonstration. It's a proof of principle at the microscopic level of what would need to be done. Okay, so if you're up with the literature, you might say, oh, but in this other recent paper, which was based on Bruckner's original theorem, with quite a similar experiment, the authors claim that their qubit is an observer or Wigner's friend. Okay, so what would make a real convincing friend or observation for an experiment like this? Is it encoding information in a simple quantum system? I'm going to say no. What about a sufficiently large or complex system? Well, maybe, but there are lots of different ways to measure those things and no clear thresholds for when you would have reached an adequately large or complex system. Okay, so for many people, a measurement or an observation has to be an irreversible active amplification. But that's not going to work here because the whole idea is we want to be able to reverse the measurement. At least we want to say quantum theories say that it's possible to reverse this measurement. So what are we left with? Well, Bruckner, in his paper, talked about an immediate experience by the friend, by the sentient observer, and I think that's actually by far the best alternative, okay? For a really, truly convincing experiment, that's what we want to aim for. So how could we do this? How could we unitarily reverse the evolution of a sentient observer? Well, it would have to be realized also with that observer being in a quantum state, that observer would have to be realized on an enormous quantum computer. And how would we know that the device was sentient? Well, we're probably never going to know, but basically I'm going to claim that it would have to be big enough, running an artificial intelligence program sufficiently sophisticated that it could genuinely be our friend. It would act like a human to that extent. Okay, so these are challenging, very challenging, and I'm not going to talk about how challenging. But if we could do all of those things, then we could have a theorem something like this, okay, which doesn't actually have superpowers. Extremely challenging, but not ridiculous, absolutely impossible superpowers. Okay, so this is the outline of the theorem. Is that we assuming again absoluteness of observations. What we're assuming technologically is that artificial intelligence at the human level can be achieved on a digital computer. That we have universal quantum computing can be done at very large scales and reasonably fast. Quantum communication, it turns out we also need that for the experiment because of the space-like separation, and that also has to be on very large scales because of the time scales involved here. But the metaphysical assumptions are the way I'm doing it here. Local agency, again, right, as we've had before. So the interesting new one is what is sometimes called the strong artificial intelligence hypothesis, which is that whenever a program that can mimic human intelligence is run on a physical computer, the computer has mental experiences the same as a human would. And that's essentially the idea behind therefore that we can attribute absoluteness of observations to that artificial intelligence running on the quantum computer. Okay, so I definitely don't have time to talk about this, but this is just to give you an idea that this is very relevant to testing various interpretations of quantum mechanics, or at least saying something about various interpretations of quantum mechanics. They all have different ideas about which of those assumptions might fail, because we know at least one of them does, except probably, I think, a Copenhagen interpretation, which I think doesn't obviously say that any of those assumptions is wrong, from which you conclude that there is something wrong with the Copenhagen interpretation. Okay. All right, so to conclude. So the take-home messages are that quantum information includes many more things than quantum computation and quantum communication, such as quantum metrology, other quantum advantages, and many parts of quantum foundations. All of these are very active areas of research, even foundations, despite what some people might think. So this last area, quantum foundations, overlaps with experimental metaphysics, which I talked about a lot. The idea that metaphysical assumptions, which are non-testable individually, can be testable in conjunction, and that's what we're doing. we're heading towards, and the ultimate vision that I talked about is that with continued advances in artificial intelligence, in quantum computing and in quantum communication, we could have a truly new frontier in experimental metaphysics, ruling out these assumptions that I talked about before. And as I said, we performed a proof of experiment in that direction. Thanks.